Recording is on. Here we are, Math 4707, Monday, October 19th. And before we get into what we were talking about previously, let me ask if there are any questions about the midterm exam that you're handing in. So this week-long midterm, it was posted last Tuesday night. It's due Wednesday midnight. No collaboration with humans, but it's open book, open web. And there were some typos. Thank you for the people who pointed out typos to me, and thank you for someone for pointing out that I needed to post it as an assignment on Canvas so that you could hand it in. I hope everybody has taken note of the typos. And are there any other typos or questions that people had about the exam that I can answer? Okay, I'll take that as a no. You can always ask me during the office hour period when we finish class. So in terms of material, we were looking at Euler tours, Euler paths in directed graphs. And let me remind you, what was the story with Euler tours? An Euler tour in an undirected graph was like in this graph, this one has one, it was a walk from vertex to vertex along edges that starts and ends at the same place, so you could close it off, and uses every edge exactly once. So this graph has one. We just drew it over here, or traced it over here. This one has no Euler tours, but it does have an Euler walk, where you start somewhere, you go along edges, and you go vertex to vertex along edges. You don't start and end at the same place, but you do use every edge once. That's called an Euler walk. And what we proved last time was a characterization of which graphs have Euler tours. A graph has with no isolated vertices, first of all. That's just getting rid of something that would not make any difference at all. If there's isolated vertices, who cares about whether that vertex was there or not, because it doesn't touch edges. And all we care about is whether we've used all the edges. So that vertex would be irrelevant if it was isolated. So assume there are none of those. Then a graph has an Euler tour if and only if it's connected, meaning any two vertices, you can find at least some path between them in the graph. And every vertex degree is even, okay? And so we went through the proof of this. It wasn't too hard to see the forward direction. The forward direction was relatively straightforward, although the fact that every vertex degree was even was an interesting argument. Just to remind you, the way that worked was when you follow the Euler tour and you focus on how it visits a particular vertex V, it visits it by having the tour come in along an edge and out along an edge, and it pairs them off. Then it goes in along another edge, out along another edge. And then it wanders around in the rest of the graph, comes back to that same vertex, comes in along an edge and out along an edge, keeps pairing them off, and therefore you have to see an even number of edges around that vertex if there's going to be an Euler tour. So the vertex degrees had to be even. It has to be connected so that the tour can actually get everywhere to all of the edges. And we also gave an algorithm that showed the backward direction. That's somehow the more interesting direction in a way, which is if it's connected and all the vertex degrees are even, how can you actually produce, no, there's not a third condition. How can you produce an Euler tour? And we gave an algorithm. It basically says you start somewhere, you leave along an edge that you haven't used and then erase it. Then you move along another edge that you haven't used and erase it. And you keep doing this until you get stuck. You enter a vertex where you've used all the edges that were touching it to get there. And you realize, because of this even edge condition, you can only get stuck at the vertex where you began. That creates a little tour which might not use all of the edges, but now you repeat this. You take out the ones that you've used, and you still have a graph with all even edges, and you break it up into these tours, and then you splice them all together at the end. So this is sort of an interesting constructive algorithm. So any questions about that algorithm before we move on? Okay, And what I had asked you to do was think about a little bit of group work that we didn't have time to do last time, but just on your own in the intervening days, to see if you can come up with the characterization, which is in the book, so you could look it up, for which are the graphs like this one that don't have an Euler tour but do have an Euler path, one of these things. And did anybody look it up or think about it? You know, what's the characterization? So how do we characterize those graphs that have an Euler tour, excuse me, an Euler path but no Euler tour?
Would you have two odd degree?
Just stop.
Sorry, I think I heard two people there.
He said only two have points have odd degree.
Right. So the characterization is you have to have exactly two vertices of odd degree. The graph still has to be connected, which, you know, you somehow think of as like the trivial part of characterization, but one should say it. And again, we should eliminate the possibility that there's isolated vertices around. They're irrelevant for Euler tours and Euler paths. Yeah. So that's the characterization that you'll find. So let's just write it down. Okay, theorem. G, let's see, an undirected graph, but I'll just say a graph with no isolated vertices, same as before, has an Euler path, but no Euler tour. If and only if. And then it's just the very similar two conditions, A and B. One of them is about G being connected. And the second one is exactly two of its vertices. Maybe I'll call them V0, V1, have odd degree, all the rest even. Oops, odd degree, all others even degree. And let's just go back to our example, right? This graph here, when we looked at it, no, not that graph. That's not one that has it. Yes, this one. This one has a Euler path, but no Euler tour. There's a question in the chat. No, connected is not the same as no isolated vertices. Connected is much stronger because connected is saying that not only do you have no isolated vertices, but here's, let me give you an example. This thing has no isolated vertices, but is not connected. Oops, I'm trying to write in red. Right, every one of its vertices at least has one edge to someone. But you can't get from, say, the square connected component to the triangle connected component. In fact, we'll talk about that later, breaking up graphs into these things called connected components. Answer your question, Jack? Yeah, you need a path from V to V prime, right? So for example, this V and this V prime have no path between them in the graph. Yeah, good. Okay. So what we were saying is an example of one of our graphs would be this one, and let's just write down the vertex degrees to check. Here, this vertex has degree 3, this one has degree 4, This one has degree 4. This one has degree 3. This one has degree 2. And this one has degree 2. And the other part of the story, we didn't actually say it, but let's put it into the statement of the theorem. We left out something that's interesting about this, is notice this Euler path, its beginning point and end point, those two, right? They are exactly the odd degree vertices. And that has to be. It comes out in the proof. So let's say that. Furthermore, every Euler path in G will start and end at those two odd degree vertices. Okay. And in thinking about the proof, let me just say that there's more than one way to deal with it after one has done the previous proof that characterized the Euler tours, the graphs that had them. So proof 1, this might be the way that people thought about how to prove it if you thought about it at all. And that is, you just do the same proof as in the other case, but you make sure that you start at V0 or V1. Well, there's two directions. First of all, the forward direction is very similar to the other proof. When you're trying to show the forward implication here, like this, the Euler path, again, will connect every pair of vertices. That's not too hard to see that every pair of vertices, you'll be able to follow a subset of the path and get a path between them. But this condition, right, if you think about it, that Euler path will give you, if you're not V0 and V1, it will pair off the edges coming in and out as the path goes through you, perhaps multiple times. If the path goes through a vertex k times, that vertex is going to have 2k vertices, 2k edges coming out of it, which is even. But if it's V0 or V1, it's actually going to have 2k minus, well, let's see. The point is the path, even though it starts there, it may come back several times. If it starts there and then comes back k times, it's going to go in and out in those 2k traversals. So there's going to be 2k plus 1 vertices that it's attached to. So the forward implication is very similar. And the backward implication, the algorithm that says if you satisfy these two conditions, how do you know there's an Euler tour? It lets you construct it in the same way as long as you start by going out from either V0 or V1, the two odd degree vertices. You have this same algorithm that says, you go out along V0, you keep going until you get stuck. And the point is, now you're going to get stuck at V1. In the very first stage of the algorithm, it's going to find a path from V0 to V1. And this is the same argument that we did before. I'm not going to write it down, but let's just say proof 1 is similar to the Euler tour proof. Okay. Proof 2 is actually kind of fun. Did anybody come up with a different way of proving it that wasn't really the same as our Euler tour proof? There is kind of another tricky way to handle it. Anybody come up with a different proof? Well, let me show you one that says, suppose we believed it for the graphs that all have even degree. Put this down here. Oops. So proof 2, take this guy, G, and add an edge from V0 to V1, like we have over here. So here was our V0, say. Here was our V1, and it doesn't matter which one I call V0 or V1, just arbitrarily number them like that. If we add in an extra edge, that's kind of small. Can you see that extra edge? Let's make that extra edge red. If you add that extra edge from V0 to V1, you've converted it to a graph that now has every vertex degree even. And it's still going to be connected. If this one was connected, that one's going to be connected. But now, create the Euler tour here. And remove the extra edge. To get an Euler path. In the original. So whatever Euler tour you came up with, you know, that went through this whole thing. Oops, I failed. How did I do that wrong? It is possible to do it wrong, of course. Yeah, that's better. Just take that thing. That's my closed Euler tour. And now I take out that edge and I'll get an Euler walk in this one, which I don't know what it looks like, but anyway, maybe it went something like this. Maybe not. No, that can't have been right because that didn't end and begin and end here. Anyway, you get my point. So questions about this? All right, I'm going to consider that to have been a reasonable proof sketch of the Euler path, but Euler no Euler tour theorem. All right, further questions before I flip the page? And then the other thing I was asking you to think about is the directed version, because this actually leads to some interesting theorems. So we're going to want to think about directed Euler tours. Okay, so this is the first time we're talking about directed graphs or digraphs, right? We're calling a typical one D instead of G to emphasize that it's directed. Still has a set of vertices, that's these red things here. But now you don't call the edges just edges, they're called directed edges. They're sometimes called directed arcs. So oftentimes people write A for the set of directed arcs. And they have a direction, right? You know, they have two endpoints, two end vertices or end nodes, V1 and V2, but you know which way they go, from V1 to V2. Okay. And then directed Euler tour in one of these things is something like what I've depicted here. Here's my D on the left. And here I've shown you a directed Euler tour. It just says, again, you have to start out at a vertex, move along edges in the direction of the arrows, following the arrows, and make sure that you use every one of the edges, sorry, arcs, every one of the arcs exactly once. And so that's what I've depicted here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And it's a closed tour. When I say tour, I mean it starts and ends at the same place. And so we just wanted to think about which directed graphs, which digraphs have an Euler tour, a directed Euler tour. So for example, you could convince yourself that this one doesn't have one. And, oh, we're getting a suggestion from Theo. Right, for each point, keep track of two things, number of outgoing edges and number of incoming edges. That is the key. And that's going to help us write down such a characterization. Let's just look at these examples for a second before we try to write it down. So this one does have a directed Euler tour. You go here, then here, then here, for example. Oh yeah, that's what I drew here. This one doesn't have one. You try to go, say, forward like that, and then forward like that, and then forward like that. And it's like, nope, now I can't go. I'm not allowed to go backward along that arrow. I could go this way, but can't complete it. Whereas this one definitely does have a directed Euler tour. It just looks like an Euler tour itself. Okay, yeah, so Theo, did you have a suggested characterization of which digraphs have directed Euler tours? Let's see, for each, okay, yeah. Theo's saying everything with an equal amount of inputs and outputs has a directed Euler tour. Yeah, so that's the condition B, the analog of condition B in the directed case. So in fact, there's a name for this number of edges incoming and number of edges outgoing. You talk about the in degree and the out degree of a vertex. So you're saying you should definitely have equal in degree and out degree at every vertex. And what about condition A? Theo? Yeah, you still need it to be connected, and connected in the old sense. It actually doesn't matter if you impose the condition that every vertex has the same in degree as its out degree, then connected in any sense of connected, actually, they're all equivalent, it turns out. So I'm just going to write this theorem. A digraph, that's directed graph, is VA, again, with no isolated vertices, just to get rid of this condition that doesn't really matter, has a directed Euler tour if and only if A and B, D is connected in the undirected sense. It's also connected in the directed sense, actually. Connected in the undirected. Let me explain what I mean by that. So connected in the undirected sense means I'll let you use the arrows in either direction. I don't even care whether you go with the arrows, but between any two vertices, you can find some path between them, even if you have to reverse arrows. In the directed sense means any two vertices actually have a directed path from one to the other, okay? And there's even something that's called the strongly connected sense when you have a directed graph. Any two vertices have a directed path from V to V prime and back from V prime to V. Those are three different notions of connected for digraphs. Some digraphs have one but not the other. They're related by implications. But in the case where you have condition B, they turn out to be all the same. Every vertex V in V has in degree of V, and I'll explain what that is, equal to out degree of V in the digraph. And so what is this thing? This is number of arcs emanating from V. Emanating just means going out of. So they look like this. Here's V, here's an arc going somewhere like that. And this is number of arcs entering. I don't know why I did a colon there. Number of arcs A and A entering V. So the arcs that look like this. Okay. And let's just go back to our example to make sure we believe this. Oh, Rory's saying something. This feels backwards. Shouldn't in degree be the number of... Oh, what am I saying? Yes, absolutely, Rory. I've got the words exactly backwards. Sorry. Let's try this. Out and in. I don't want to erase all my purple stuff. Thank you, Rory. Out, emanating, in, entering. Thanks. Let's go back to our example here, right? I'll do the in degrees in green. This one has in degree 1. This one has in degree 2. This one has in degree 1. This one has in degree 3. Yeah, 3. This one has in degree 1. This one has in degree 2. This one has in degree 1. And actually notice they're equal to the out degrees because this one does have a directed Euler tour, right? I don't have to check, but we could check, right? This one also has 2 coming out. This one also has 1 coming out. This one has 1 coming out. This one has 3 coming out. This one has 1 coming out. This one has 2 coming out. And this one has 1 coming out. The in degrees are equal to the out degrees. And they're written in green what they both are for every vertex. Everybody see what I mean? And this graph is definitely connected in any sense of the word, right? If I want to get to from this vertex to this vertex, I can certainly go like this, ignoring the arrows, right? There I went against one of the arrows. This one was going backwards, but I don't care. I claim that when you're in a graph where you've got in degree equal to out degree at every vertex, if you had paths like this, you're also going to have one that follows the arrows like this, from this vertex to this vertex. And backwards, you're going to have a path from that one to that one that goes with the arrows, forward and backwards. So all the notions of connectivity are the same in those kinds of diagrams. And these are called Eulerian digraphs, the ones that have these two properties. Let me just take that picture of our favorite Eulerian digraph here so we can stare at it. And let's think about why this one is true. So can we actually prove that this characterization? Does anybody have any thoughts on how to prove this theorem?
You can prove the forward direction pretty easily. Like to connect any two vertices, you just go along the Euler tour until you just hit the vertex that you need. And then for part B, you can prove that you can just think that the tour it visits, whenever it visits, it goes in once and it comes out once. So every visit adds one to the in degree and 1 to the out degree at the same time.
Or removes one from the, yeah. Oh, I see. You're thinking about why does B, sorry, you're still doing the forward direction. Why?
Yeah.
Yeah, that's right. Yeah, so let's think about it. In the forward direction, it's the same proof as to why having an Euler tour makes you connected. Yeah, you can follow the path through the Euler tour. It's going to get from V to V prime at some point because nobody's isolated. V and V prime have some arcs that touch them. So the Euler tour is going to go through V, and then later it's going to go through V prime. And yes, again, the Euler tour itself, as it enters and exits V, it might do it k times, but then that's going to make the in degree k and the out degree k. So it is the same proof, actually, for the forward implication. Everybody see why it's basically the same proof. Just thinking about in degree and out degree versus degree. What about the backward direction? Suppose I have a digraph in which it's connected and every vertex has the same in degree as out degree. How can I construct a directed Euler tour? Let me hear
it's really
from
similar
somebody
also,
else.
isn't it? Oh,
Yeah, hold on, William. Let me hear from someone else. Anybody see how I could construct a directed Euler tour if I've got conditions A and B?
Would it be possible to do a similar sort of like just start until you get back to your starting place and then suture on new loops?
Yes, it would.
Than
Right.
that.
If you think about it, it's the same proof. I mean, it really is just the same. You just pick an arbitrary vertex V0 to start. You cannot go wrong in this situation. Just pick somewhere and say, oh, I'm going to leave along one of its outgoing vertices. Excuse me, along one of its outgoing arcs. You enter someone else and you leave. You just keep trying to do this until you come back to the same place. Okay. And what did I do? I just created, ooh, I forgot what I did. Anyway, I just created a little tour. You convince yourself that you have to come back to the same spot. Once you get stuck, you must have come back to the vertex you began with, because everybody else, as you enter and leave beside that first one, you remove one from its in degree, you remove one from its out degree, it stays even. The only one that you could get stuck at and have nowhere to leave is that first one, where you left it with along an edge, and then its in degree was one greater than its out degree. So again, the story is you build a tour, as Rory was saying, that doesn't use all the edges, but now you take these remaining ones, I don't know what it looked like. Anyway, you take the remaining ones and all the vertices have in degree equals out degree because you took out a tour. It keeps in degree equal to out degree if you remove a closed tour. You build tours in the remaining pieces and suture them together. It is the same proof. So essentially, it's all the same proof. That's all I'm going to write.
So there's the abbreviation digraphs for directed graphs. Is there an abbreviation for undirected graphs? Because that's a lot to write.
Sadly, no. People, you know, when they say graphs, usually they mean undirected. There's nothing like undigraphs, sorry. Yeah. Okay, so that's all I'm gonna write. I don't wanna bore you by, writing a million things, but feel free to ask me in office hour if you didn't understand part of that. Is there anything I can explain now about that proof that was not so clear? Okay. So why did I have a blank page here? I don't know. I think I wanted to do this. Yeah. Yeah, I wanted that blank page back there. Let me take this out. Put this up here. Good. So we just talked about Eulerian digraphs, and what I want to show you is something that it's related to. Eulerian digraphs actually come up in various applications. This one's going to seem like a very fake application, but it's related to ones that people do. So I once went to a talk by a famous mathematician who started out life as a magician. His name's Percy Diaconis. I don't know if people have heard about him or not, but this is actually an interesting guy to look up on Wikipedia. There's actually books, where people have interviewed him and stuff. He's quite a character. And so if you look on Wikipedia, it will tell you the story about how he basically dropped out of high school to become a magician. And he studied with some particular famous magician. I don't remember the person's name. Oh, Vernon, I think, Dal Vernon. And he really liked various kinds of sleight of hand and card tricks. And he can do certain kinds of physically nearly impossible things. He's quite adept. But I watched him give a talk in which he does the following card trick. So I'm going to try to explain it to you. When I teach the class, usually I actually do the card trick, but although there's some parts of it that I just cannot reproduce quite the same of what Diaconis does. Okay, so when he gives the talk, here's the way he describes doing the trick. He says he's in some bar, wherever, performing magic, and he pulls out a deck, okay? and he shuffles the deck. So he like shuffles it a few times. I am shuffling, see, I'm shuffling, you know, shuffle, shuffle. Did you guys hear that shuffling noise? That's me shuffling. Okay. And then after he shuffles it a few times, he puts a rubber band on the deck because he's about to throw the deck into the audience and ask the audience members to do something. And so he like chucks it into the audience and somebody catches it, okay? Some random person. He doesn't like try to get a particular person to catch it. Now, the first thing one has to realize is even though he shuffled this deck, there are two ways in which Percy Diaconis can create a prepared deck that looks like it's been shuffled. One is a really interesting thing about him is he knows how to take a deck that he's already prepared and do a perfect riffle shuffle in which on the left side, first of all, he can cut the deck exactly in half. If it was 52 cards, he can cut it 26, 26, and then drop left, right, left, right, left, right, a perfect riffle shuffle like that. And then he knows how many times you have to do a perfect riffle shuffle until you get back to the original ordering of the deck as if it was prepared. So this is already one amazing thing about him. But the easier way in which he does this trick apparently is after he shuffles this deck, he's got another prepared one up his sleeve and he gets rid of the one by, you know, palming it. So basically he throws this prepared deck into the audience, all right, with the rubber band around it. Then he says, all right, you first person who caught the deck, take that rubber band off. And he asks them to be very careful about this. And he says, you know, when he's in a bar and people are drunk, he has to make sure that he has a second deck ready to do this, or maybe a third deck because, you know, people will somehow muck with it and not follow his instructions. But whoever catches it, he says, please do a cut, you know, a usual cut of the deck. In other words, break it somewhere and put the bottom on the top. Or if you like, break it somewhere and put the top on the bottom. There's no difference. Anyway, and then he says, now hand it to the next person who's sitting to your left or whatever, have them do a few cuts like this. So they do a few cuts. And then he lets any number of people do some cuts, but he's carefully watching to make sure that they cut it properly. You see what I'm doing? That they really just break it somewhere and put it bottom on top. Okay, then when everybody's satisfied that he doesn't have Confederates all around the bar who cut for him nicely, that it's really been cut several times randomly, he then says, all right, the person who's holding it, you take the top card, don't show it to anybody, hand the deck to the next person who takes the next card, don't show it to anybody, hand it to the next person who takes the top card. 5 people like that. So he's sitting there with 5 people. You can't see this, but here they are, the 5 cards, all right, with the 5 people. And he then says, okay, what I want you 5 people to do is to really, really think hard about your card. I mean, think about it, concentrate. Don't show it to anybody, but concentrate really hard. And then Percy himself starts like concentrating really, really, really hard. He's trying to guess their cards, okay? He says, okay, I'm not quite getting it, but the red cards, the mental signal is stronger from the red cards. I want the red card people, whoever has red cards, please stand up and concentrate really, really, really hard. And so maybe number 2 and number 4 and number 5, they stand up and they start concentrating really, really, really hard. And the first and the third person, they're still sitting down because, you know, they were failing to send him the mental signals. And then after 1, 4, and 5, you know, start sitting there concentrating on their card, he just names each of the 5 cards in order. He says, you got the 7 of clubs, you got the 10 of diamonds, you got the, you know, boom, 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 and gets them exactly correct. Okay. And so when I do this trick, I don't try to shuffle the deck. I don't try to palm anything. I walk in with my prepared rubber banded deck. And I hope that people don't notice that there's actually not 52 cards, there's 32 cards. And then I throw it into the classroom, and then the rest of the trick proceeds exactly the way I said. And it's amazing. You guys would think I'm just incredible if you saw me do this trick. I have never failed. I've practiced it many times. Have a deck of only aces of spades. No, there are actually 5 different cards that he guesses of those people when he gets it exactly right. It's not all aces of spades. But of course, it is a prepared deck. And what I'm going to do is show you how the deck has been prepared, except I have to make sure we get our, I lost my screen broadcasting here. Start the broadcast. All right. Get back to my page where some of you may have seen it already. So I'm showing you how the deck has been prepared. It's a deck of size 32. It's got 32 cards, and this is one way to prepare it. This is the one that I usually prepare it with, is these 32 cards in order. 7 of diamonds, 5 of hearts, 4 of diamonds, jack of diamonds, king of hearts, 7 of, etc. You see it like that sequence of cards? Okay. And the point about that sequence of cards is I want to think about which ones are red and which ones are black in this sequence of cards. And when we come back from the break, I'll see if anybody can figure out what's good about this preparation of the cards that lets him do the trick. So we're about to take our 10-minute break. Any questions before I turn the recording off? I see something in the chat there. No, that was the only ace of spades comment, right? Any questions before I turn off recording? Okay, so we'll come back at like, what is it, 3:23. I've got about 3:13 right now.